Welcome. Thank you very much for joining our session. We're going to talk today about Game of Inches. That's the title of our session. And what we're talking about is digital as-builting of a 27-year-old NFL stadium. We're super excited about this project, and we can't wait to share it with you all. So first things first, we want to talk about the objectives of this session. What are we trying to teach you all about? The first part is facility needs. Any facility requires a lot of different needs in terms of maintenance, in terms of renovation and expansion. All of these different things that happen throughout the life cycle of a facility require data, requires information about the facility itself. So that's a very important need to understand. And most of the facilities that we have these days are run through papers, as-built documents that's been submitted years and years ago. The second part of it is reality capture. So reality capture tools and how they are important into capturing all of the existing conditions of each of those facilities that help the facility needs and looking at future uses. The next part of it is Scan-to-BIM. So reality capture solutions usually give you a point cloud or just photos. How do you take that data and actually put it into a model that the facility managers can then use throughout the facility lifecycle? And then the last part is innovation. Constantly looking at new technologies, new ways of capturing, new ways of modeling, new ways of sharing, collaborating. All of these different technologies are constantly evolving. So you need to be in the front line of that. You need to be testing new things and looking at new technologies. So these are the four main objectives of our class. Let me start with introducing myself. My name is Hamza Shanbari. I'm the Director of Innovation at Haskell. Come from an academic background, have my PhD in Design, Construction, and Planning from the University of Florida. Worked for about 6 years now with Haskell, started at the Virtual Design and Construction group with Ryan's great group, and then transitioned into this kind of innovation and technology role. I'll let Ryan introduce himself.
Yeah, Ryan Kamer, Director of VDC. So have been working at Haskell for the last 15 years by way of Purdue University. I lead our VDC business unit as well as our reality capture, which is laser scanning, digital layout for self-perform mostly, as well as our drone services business unit. So 5 years ago, we brought in laser scanning in-house, and since then we've executed over 100 projects internally over that course of time in the last 5 years or so. We also, in our group, support clash detection, model-based estimating, virtual reality, visualization services, in addition to the layout, laser scanning, and drone mapping. This will be my third time that I'm honored to present here at AU. I've also done some presentations for other organizations, ABC, AAA, DBIA, and ENR, and guest lecture from time to time at UF and UNF.
Awesome. Thank you, Ryan. So let's talk a little bit about Haskell. Haskell is a design-build firm based out of Jacksonville, Florida. We're going to talk all about Jacksonville today. Founded in 1965 by Preston Haskell, who you see his picture here. He's also actually one of the founders of the Design Build Institute of Florida, or Design Build Institute of America. I always say that. We are a very safety conscious company. We have a very good RIR of 0.17, and it's still not good enough. Of course, we're still striving for that zero incident that we'll hopefully get to at 2025. 100% employee-owned company, $1.4 billion in revenue, a little bit over 1,800 employees. That's constantly growing. And then the other thing that we constantly pride ourselves in is 80% repeat business. We also have a very concentrated, heavy look at training, and we've ranked number 3 in Training Magazine's Top 100. So we're also very proud of that. A little background on Disruptech. So Disruptech is Haskell's venture capital arm. It was founded in 2018. And what our mission is mainly consists of 3 different pillars, right? So it's invest, invent, and innovate. We make investments in the space, in the construction technology space, when it makes sense for us. We do have a dedicated R&D center, and we kind of have that R&D hat where we try and actually make things. And then the last part is the structured innovation program, where we open up the floor for all our employees to kind of submit ideas and look at how do we implement it, whether it's in the design side, in the office, or in the field, and the job site. So a little bit about Jacksonville. Jacksonville, if you're joining us, especially if you don't know anything about Jacksonville, Jacksonville is a great city. It sits in the northeast corner of Florida, United States. If you're, from international countries, very hot, and actually Florida is known for being the sunshine state. So it's always very hot and humid. We have lots of bridges as well. It's something that's really interesting that cross the St. Johns River. We have maybe 9 or 10 of them. And we are very central and very heavy on NFL. So NFL is the National Football League, and it's an American football league that's played differently than soccer. Do not confuse football with soccer, because I know there's a lot of international audience here. But the Jacksonville Jaguars is our team, and they play in the league, and we have a good team. We haven't won any championships yet, but we're getting there, and that's kind of where we're really kind of trying to push forward this city and this team as well, with going to the Jaguars' future, right? So we're all kind of collectively cheering on this team that we're trying to take into the future and hopefully win championships in the near future. And that kind of gets us to the problem statement.
Yeah, so the problem that our client brought to us, which was the Jaguars, was how do they properly document what they have in order to prepare for upcoming renovation expansion needs. And those needs, per their fans, were increased shade and rain coverage, wider concourses, improved airflow, upgraded MEP systems, better vertical transportation, and then increased space for football ops, which you see in the lower left-hand corner, courtesy of Rossetti Architects. So that one is actually being taken care of today. So Haskell, working with Rossetti Architects, is actively building a new sports performance center, now called Miller Performance Center, to house all of that state-of-the-art training equipment, as well as a fan amenity center. So that is underway, as well as some future renovation expansion efforts. But historically, the as-builts are not all digital, so that makes it hard to understand the current design to prepare for the future, based on renovations over years since it was built 27 years ago. So they need an accurate representation, and that's where Haskell comes in. So we're a partner with the Jaguars, having worked with them on many projects. We actually worked with them to build the initial stadium in '95. We're located 2 miles away west of them, across the St. Johns River bank that you see there. So we talked about what they need and how we can help them. The existing conditions model was number one. So we needed to document all those changes and additions over time. We wanted to ultimately convert all that into Revit models that are up to date, especially the architectural and structural elements. Then we wanted to downstream all of that data to the awarded AC team for any new renovation expansion projects to come, as well as all of our raw data collected, scan data, point clouds as well in that process. So our approach, so we looked at all the limited record drawings we could get our hands on in digital format, some Revit models, some not, some PDF, some AutoCAD. And we looked at an approach to laser scan the entire facility, inside and out, every nook and cranny, and leverage that point cloud data to generate ultimately an as-built model and share that downstream with the AC consultants. So our game plan here essentially was in 4 phases that you see there, to establish the ground control points and tie that to the terrestrial ground scan data. We also wanted to leverage SLAM scan as best as we could. So SLAM is simultaneous localization and mapping, if you're not familiar with the acronym, so which is mobile scanning. So a facility of this size, that could be a huge benefit. Anything we can do to increase the speed of scanning such a massive facility. And then drone mapping needs due to the elevated structures and towers for scoreboard towers, light towers, camera towers and such, as well as just the drone mapping of the site itself. And then the Scan-to-BIM ultimately was the final phase of this process. All right, we'll start with the terrestrial scan approach. So it's important to have a solid game plan going into our terrestrial scanning process. So we developed, in this case, and on every project, a scan map. So we took all of the ultimately plans that we had available in PDF format. Sometimes we needed to cobble together other plans in order to create the closest current as-built document. And then we populated that with our scan markers to document where we want to scan, using rules of thumb for scan spacing, scanning in each door threshold, different scan markers for above ceiling scans where needed, where we knew there were drop ceilings or maybe access panels and such. And then that scan plan informed our estimate on how long we expected this process to take. We also knew that we had to coordinate with COVID protocol requirements at this time, since this was in really the early phases of COVID-19 across the country and across the world. So as far as the on-site execution, the terrestrial laser scanning effort, that took about 5.5 weeks. So we had a daily check-in with the client. We would update them on scan progress continuously. We'd talk about access needs and look ahead where we need to get to next, what's available that day or that week. We constantly needed to revise our game plan based on what was happening in the facility and where we could gain access, where we could not, and kind of alter that plan on the fly in order to make sure that we were continuously scanning. We had a 3-man scan crew at all times. We had an on-site project manager and 2 scan technicians, using a total of 4 terrestrial laser scanners, a Trimble SX10 from left to right on the bottom of the screen, as well as a Trimble X7 laser scanner. We also were running 2 Faro Focus scanners for the congested spaces mostly. So that Trimble SX10 scanner, which is a scanning total station, so that provided our control network and really the backbone of all of our terrestrial scan data to tie to that initial control and localize on that ground control network. From there, the Trimble X7 scanner was our most widely used laser scanner. This did the bulk of the scanning for us. A really nice feature that it had was automatic survey grade level compensation. So this facility has ramps and constantly changing elevations throughout. So that was important for us in the scanner we're looking at selecting for this project. Also has visual confirmation. So it does have a tablet paired with it, which is very nice. We can check and see what we scanned, confirm that we captured what we needed via line of sight. Also has some automatic registration functionality, so it can link up to the previous scan and reduce the back-end time needed for that scan registration ultimately. The scan setting we were using was about 2.5 minutes for a full color scan that may be stationed roughly 30 feet apart from each other. In addition to that, as I mentioned earlier, we're using Faro Focus scanners. So we had typically 1 scan operator operating those in pairs and leapfrogging those 2 scanners throughout hallways, office space. We used them in many of these congested areas, as well as above ceiling scanning. This scan setting we used was about 5.5 minutes per each scan, and then half that really for the black and white scanning. So we did not need full color scans when we were scanning above ceiling. That could be done in black and white. Door thresholds necessary simply to tie rooms to each other. That was also more of a quick scan, black and white scan for our purposes here. There are a number of different obstacles throughout. The interstitial space below the seating was challenging to get to in some cases. As pictured here, we needed to scan on top of a room to actually see those precast elements that we're looking for above the precast raker beams that you see there. It's the sawtooth beam with the seating precast tees sitting on top of that for the seating. So yeah, in many cases we need to get creative, find access ladders to get above certain rooms to see the structure underneath, and tons of nooks and crannies unanticipated going into this effort that we had to really get creative from the field team on site in order to gain access where needed. Here's a look at our above ceiling scanning process. So we used an elevating tripod that allowed us to crank the scanner up to as high as 13-foot elevation. So we scanned above all ACT ceilings and access panels where we could access the ceiling to see the interstitial space above, and most importantly, the structure above. In many cases, we would pop ceiling tiles. It would be too congested. We'd have to try again, pop a ceiling tile on a less congested space to try to see more data. So that was a constant slow-moving process with the ceiling tile removal, the crank-operated tripod scanner, using a ladder, for access as well. And then as you see pictured below, We would crank the scanner up to just below ceiling tile, complete a scan, and then crank it up to max height without hitting any elements, unobstructed elevation. And we would tie those two scans together on the registration side vertically, and then we would tie the scans together horizontally below ceiling. That allowed us to tie everything together, since we knew we may not have line of sight above ceiling from scan to scan. We had to tie those together below. We also knew portability would be a consideration and an issue, so we wanted to have power at all times. So we purchased a battery charged power generator. We had that on a laptop cart so that the laptop always had power on site. So the project manager who was coordinating access to areas could also be registering the scans that he received daily on site through that laptop cart. We also had several scanning carts for all the scanning gear, the sphere targets that you see pictured there, as well as any drawings, any tablets for access to drawings digitally, and for marking our progress. Overall scanning stats, here's a look at the numbers. So all in all, it was 25 days of the terrestrial scanning on site, completed over 7 weeks time. We did have a total of about a week and a half of downtime. So there were actually the NFL draft took place while we were scanning there, and there were rooms and entire days where we could not access. There were also other events. So there were concerts and other events happening that we needed to log as off days and could not access the facility to scan. But over the course of 7 weeks, we ultimately completed 25 days of scanning out there. It was approaching 3,600 total scans, which was our largest scan project to date with those 4 scanners. And then on the back end, it was about 46 additional days to complete registration, stitch together all that data from multiple scanners, even though we did have some of the automatic registration happening and manual registration as well on site. And then total is about 2.2 terabytes of scan data in the recap files that were ultimately linked in for modeling in Revit. And we split those files up into 52 zones, which was necessary to reduce the file size to looking at certain areas, certain chunks of scan data at any given time based on file size. Here's a look at some of that terrestrial scan data that you see here. You saw some of the exterior outside the club area. Now we're flying through a concession area called Daly's Place in the south end zone here. So you're seeing some of this is actually the most wide open, I would say, of all the spaces we scanned. Some of the easier scanning that we did, and you can see some of the structure that we're looking to capture above all of the columns, beams, masonry walls, precast seating above. We're continuing down through some of the main concourse areas, through some of the lower structure areas here. You can see some of the congestion there as we pass through, heading out to a tunnel now, and several loops inside the stadium completed as well from there, just to give you a sense of the data.
All right, that was impressive, isn't it? That's a lot of scans and a lot of days. Moving on to site mapping. So this is drone site mapping. This isn't like our drone SLAM scanning yet. We're getting there, but this is to map the entire site. And what we used is a Phantom 4 RTK was the main unit that we used, and that was done top-down view, just flying around the job site and capturing all that data so that we can get site information, right? We also did some of the inner bowl loops and an exterior bowl loops too, so that we can capture the facade and the interior of that facility. But overall, everything was also kind of captured using propeller arrow points as our kind of ground control points. And we like to put that, center point on the 50-yard line. If you know anything about American football, that's the center line of the field, with also some additional arrow points around the site, right? So you have to spread them out so you can get that good geolocation of the entire data. Moving on to SLAM scanning. So why did we even get to SLAM scanning is because of all this high structure around the stadium, especially those huge light poles. A lot of that data could not be captured by either the terrestrial scans, because those are just too high up in the air, or the Phantom 4 RTK, because photogrammetry works a little bit differently than actual scanning. So the data that we got out of that from a drone photogrammetry aspect were not sufficient enough and were not detailed enough. So we needed to get a drone with a SLAM scanner on it, so we can capture those details higher up. And the plan, again, is like we always emphasize on planning, right? Failing to plan is planning to fail. So we don't want to do that. We want to plan accordingly. And the plan here was to use an Emerson hover map on a DJI M300. And the flight plan internally was to do 4 different sweeps inside the bowl. So 1 for each section, so north, east, south, and west of the inner staging area or seating area. And then 4 externally, looking at the facade from the outside, right? So the same thing, east, west, north, and south aspects of the building. We also utilized, again, the propeller arrow points to geo-reference that data and actually tie it into everything else that we were doing. Another cool part is we said, all right, we're SLAM scanning the exterior using a drone. Why don't we also do it using a robot? So that's kind of like a nice to have additional information that we can get from the interior and all these different interstitial areas that Ryan was talking about that they captured with the terrestrial scanners. Execution. So we got to the facility the day off, and of course you have to assign a great remote piloting command. And in this case, we had Pete Kelsey. Thank you so much, Pete. This was the most professional remote piloting command that we've worked with so far. And we had 2 visual observers. So Andy Justicia from Aerodyne Measure and myself kind of worked constantly with Pete in order to kind of communicate what's happening with the drone. So we're all having different point of views and different line of sight angles with the drone, so we can constantly communicate via radio, whether Pete can, move closer to an object or just stop or hold back. And we worked really well as a team, kind of trying to guide that flight and capturing of all that data. And of course, safety is super important. So we spent 1 hour of prep before we even got the drone out of the case, right? Because we're talking about safety aspects. We're talking about what could go wrong, all those risk mitigation techniques and measures that we're putting in place. What would we do if this went wrong? So we had to talk about all of that and sign a piece of paper saying we all understood the risk associated with that and how to mitigate that. And then the actual scans, they were like 30 minutes each for each section of the interior bowl, and then each section of the exterior as well. The coolest thing is what we were able to process the data while we're scanning as well. So every time we would finish a section, Pete would bring the drone back. We would stick the USB thumb in there and get the data out, put it in the computer, and let it process while we're doing the other scan. So that was really cool to see the scan as we were kind of capturing more scans. And then when we went back to the outside, especially in the area where it kind of connects with the Daly's place, that was a much more intricate flight, because there's a lot of different elements and steel and connections between the different buildings that we really had to kind of guide the drone throughout. And it was a pretty cool experience to be able to be part of that. Results is what we captured is 8 separate scans. And this is just focusing heavily on what we got from the Emerson hover map and the drone. Again, as we said, 4 inside and 4 outside, totaling 440 million points with, again, as Pete always likes to say, like virtually no drifts, which was great, with 4.3 gigabyte data size. And this is all just the SLAM scan from the Emerson hover map. So we're going to look at the video of how we captured that. And if you saw one of the pictures over there that we had the video crew with us that actually helped us capture all of that.
All right, great video. Impressive work on the SLAM scanning side. So now to the Scan-to-BIM. All right, so we now needed to come up with a modeling strategy. So we decided to create two separate models, a structural model and an architectural model, as well as two separate teams for architectural and structural. We were working from the ground up by zone. Generally, each zone was broken into quadrants by floor, sometimes further. The structural modeling team was modeling mostly precast elements, so precast columns, raker beams, the precast seating, also the structural steel towers, columns, beams, and a number of infill structural steel joists as well throughout. The architectural team, we broke out to model floors, walls, ceilings, doors, windows, stairs, ramps, escalators, and such. As far as the record drawing documentation from all of that, we also put together floor plans, section drawings, ceiling plans, and 3D isometric views. Overall, on the Scan-to-BIM stats here, we did this in 12 weeks of modeling for the structural and architectural modeling scope with 13 team members. We had 6 modeling full-time and 7 helping out part-time. Over 2,200 hours of modeling, 635 by the structural team and close to 1,600 from the architectural team. So substantially more from the architectural team due to all the office space, all the press boxes, suites, club areas. So there's really a lot more underneath the stadium than you realize. That is a lot of architectural scope. And in total, the structural and architectural team had a separate weekly meeting for those 12 weeks, and we had a combined weekly meeting. Those were our internal reviews. So 36 meetings in total, looking at model accuracy throughout those 12 weeks. We selected the platform Cintu that you see here. So this is a web-based application. We could host all of the scan data, all the 360 photos here on the Cintu site. So we created some area breakouts per level and per some of the quadrants to be able to sort through this massive amount of data a little faster, so the modelers could jump to a specific level, specific area that they're working in to model. Similar to Google Street View, also comes with an overview map to see all of the 360 photos at those scan stations. So similar functionality that you have in Autodesk Recap, just in a web-based application here, in order to navigate, help the end user, in this case, who's the modeler or designer, work with this scan data. Also includes the 3D view, which allows you to view the point cloud or 360 photos in 3D. So you can walk or rotate here, see the point cloud data or see the 360 photo itself. Here we're looking at a concession area called Daly's Place, in front of the Daly's Place amphitheater on the south side, near the south end zone. And we also have the ability, you see there on the left, all those 3,600 scans, we can also toggle on Revit models in progress. This is a really handy feature, so we could see how we're doing on the modeling side and see if it's matching the scans, and use that to facilitate the model reviews we're doing on a weekly or sometimes multiple times in a week basis. So here it includes a really nice couple features, some visual comparison tools. So one is the visual difference tool. It includes a red-green color coding. You can dial up the tolerance you're looking for to colorize that red-green. It's also showing us what's colored red is not modeled at all. So that helps us understand what we've modeled, not modeled, and if we've modeled it, did we meet our intended tolerance. Also has another visual check tool slider, which you can toggle on the transparency settings. So you can turn it from opaque to fully transparent to see only the 360 photos or only the Revit models. So using these two tools in tandem was really helpful for our modeling team and for our QC review team throughout the process here in this Cintu platform that we selected. We also tied the Cintu platform, not just loading the models, but loading them to BIM 360, so that those those live RVTs in progress, those Revit files, could be updated in the Cintu environment. We linked that as well, Cintu, to BIM track. So as we're tagging issues, we could publish that into a BIM track report. So these are some of the examples of the QC checks we were doing and what we caught and how we would help inform our team of things that needed to be corrected in the model. So on the structural side, from left to right, we caught some of the precast modeling that was not tight enough, so that that precast T there for the seating needs to be deeper to match the point cloud. So we would identify that as an issue in this process, tag it through the Cintu to BIM track reporting process. Similarly, in the middle, we might catch walls that were modeled maybe too high in the case of the wall near the stair, and we'd flag it here for adjustment for the modeler to correct that. Or this example on the right of a door missing. So the wall modeled through that door, we would flag that and identify that we had another door to pick up throughout the process. So this was really helpful. The BIM 360 Cintu to BIM track integration of all three worked perfectly in our case. As far as model sharing, as I just mentioned, so through the Autodesk Construction Cloud, BIM 360, our structural team and architectural team were able to work in sync as if they were in the same office virtually. So we were operating out of 3 different locations for our modeling team of 13, led by Aaron on the structural side, and also Aaron on the architectural side in St. Louis and Jacksonville, respectively, through the BIM 360 cloud. Here's a snapshot of the structural model. So the structural model was actually larger than the architectural model in terms of file size. It was 1.4 gigabytes. And the architectural model was another gigabyte in that 2,200 modeling hours mentioned here. This was the output. Now you see the added architectural elements. So you can see the curtain wall there near the bottom middle of the screen, and the roofing elements, and stairs and escalators and scoreboards and walls. You see the Cabana Club area on the north end there. So this is all part of that roughly 2.4 gigabytes total of model deliverable. Now here's a look on the BIM 360 site itself on some of those deliverables mentioned. So it was some of the section drawings, and this is a 3D isometric view printed on the drawings, showing the combined architectural structural effort as well as some of the plans broken out by level and by quadrants throughout to document all of this great scan data in the Scan-to-BIM process to turn over to the client. Now here's a look at the 3D model viewer of the combined models, architectural and structural. Here we're looking at some section slices to give you a sense of detail. So it may not have looked apparent just looking at the inner or outer bowl, but there's a great number of rooms and club areas and such to model here, as you see in one of the club areas. Some complex stairs and escalators and such to model. Many different ceiling elevations, some slope ceilings, some ceilings sloping in multiple directions to deal with so really some nuanced modeling needed to complete this. Now we're seeing a lot of the congested areas on the first level. So this is all the admin office space, all the player facilities, the team meeting rooms, the weight rooms, training rooms, is all down there, really between the club area and the fields. Now we're looking at just some section cuts to understand some of the complexity and nuances of this model resulting from the Scan-to-BIM effort. So we thought going into this that we could mirror a lot of the modeling, but it turned out that mirroring wasn't quite as easy as we thought. There were differences on both sides. Even the upper concourses and club areas respectively are on slightly different levels. They're close but different levels. So as well as it's more of an oval shape, so it's not a circle that we can easily mirror around from area to area. So yeah, it was quite a bit of manual modeling. It wasn't as easy as we might have thought to copy and paste from other areas. It was pretty unique throughout. Also in this platform, you're now seeing some of the walkthrough capabilities. So you can use the the keyboard to walk through first person. So here we're on what's known as the service level or the ground level in front of one of the club areas and the curtain wall you see outside of the club area. You will notice some flickering here. So this is a web-based viewer. It's pretty impressive that it is handling the close to 2.4, 2.5 gigabytes of model data here as we walk through, but there is some flickering, some regeneration happening here while it's attempting to show all the model elements on screen. So here we'll do a quick walkthrough of the club area, walking up that curved staircase from the lower club, now heading up towards the upper club level. So you can start to see what some of the the intricate details were in this facility that accounted for those 2,200 hours of modeling, and a lot of what the architectural team had to deal with here. So stairs in particular were a huge modeling time investment on this one. There were maybe close to 100 stairs. We had one of the 13 team members modeling did nothing but model stairs continuously for 12 weeks straight. So really a lot to accomplish in a pretty short amount of time, and really a great job all around by the modeling team here, and the finished product that we were able to turn over and showcase here, that you're seeing some snippets of in BIM 360.
And mission accomplished. Wow, that's like impressive modeling abilities, man. It's like the team did it. Touchdown. We didn't only just complete the scans in record time, especially around block days. We talked about the draft days, we talked about concert days, all that stuff. So there's a lot to kind of coordinate and work around, but also delivered an existing conditions model on time that's highly accurate, that's well received. We got immediate positive feedback from the client and the designers that received the model to kind of like start designing on top of in terms of next steps and renovations and all that stuff. Point clouds were also part of the deliverables. So we shared all of that stuff with the client, and then they in turn shared it with the design team that's going to take it from there, and take a look at all that data.
So a few important lessons learned. Planning and preparation obviously was essential. Going in, we didn't realize exactly how much data would be covered up by the seats. So the seats occupied that critical data that we wanted, which was the top of the precast seating, to understand our riser heights and how they would change from closer to the field and moving away to the outside of the bowl. So that was something that we didn't realize we'd have to rely so much on the aisleway scan data, since the seats covered up so much of that good data on the underside that we really wanted to see. We also had lessons learned on control. So we created mostly an outer loop of control network. Going forward, or if we had to do this again, we probably would have created a more elevated interior control network where we could set the robotic toll station up in one elevated place and then shoot an interior control network from that same spot that we could have tied in maybe quicker and easier than the outer loop that we ended up using it mostly as the backbone. We also relied on the 50-yard line center field center point, but didn't realize going in that that's not really an exact center point. I mean, it's roughly a 4-inch wide painted strip on grass, so it's not really an exact center. So we ended up virtually triangulating the physical center point between the two goalposts to get to our virtual origin, but we would have probably hard measured that if we did it again to find the exact center, since we couldn't tell that exactly from the painted lines so much.
And then, talk about game of inches, right? Talking about 4 inches line and trying to find the center point of that. So the team did a great job into finding that. But one of the other things that we quickly found out is the use of SLAM was great, but it could have come before the actual terrestrial scan. And I think that would have helped the team a lot into capturing the area quickly and help them also plan it as kind of like, where do you want those detailed scans to occur and take place. Another big lesson learned for me was sunscreens, especially working in the outside and trying to scan for hours. Uh, Protection is important. Pete was very prepared. I was not. I learned the hard way. So make sure to wear sunscreen. And the last but not least is testing new technology. Always keep an open mind about what's out there, what's coming, what's new technologies, how we can implement this better, faster, more efficiently, more accurate. There's so many different technologies out there, and the game is always changing and evolving. So just be on the lookout for new technologies, new ways of implementing and getting to that goal that you set, of course, through planning. So thank you all for joining us again. We hope you learned a couple of good nuggets here from this huge and fantastic project. I just want to say great shout out and thank you to the Jacksonville Jaguars team who worked with us and coordinating all of this effort. The great team here within Haskell, the VDC team that did a great job in the scanning and the modeling. Really, really amazing stats. If you go back and look at the numbers, they're just going to blow your mind away. Every time I look at them, I'm like, wow, that's impressive. Thank you all again, and hope to see you all in New Orleans and then get together and have a beer or two.